Good morning to all of you. For 2-3 minutes, please go through whatever I did in the last class. If you have any doubts, questions, you can ask. So, are there any questions? So, then I think let me start if there are no questions. So, are there any questions? So, last class we started dynamic analysis. So, we had developed the expressions for kinetic energy and then the equations of motion at element level. And then let us look at first some applications. So, maybe one simple problem I am going to take is say if I have a bar and let us say that it is a stepped bar, and of course, I am going to simplify the problem in terms of discretization. So, let us say that we have this bar and this portion is, say, the length is L and this is also of same length, although they can be of different lengths, and say the density is same for both this thicker and thinner bars. So, let us say density is rho, cross sectional area is, let us say, 2a here, and Young's modulus is E, and for this let us say density is same rho, but area is just A, that is half of the first one, and Young's modulus is E. And okay, it can be actually free. So, let us also say that this end is constrained by a spring and which is fixed, and the spring constant K is, let us say, also expressed in terms of these quantities. So, let us say that is EA by L. And let us also say that although there can be a distributed force also, but distributed force is 0 and there is only a concentrated force here, let us say this is P. So, first what we want to do is we want to set up the equations of motion for this. So, here P is a function of time. So, this vibrating rod. So, now first step would be obviously discretization. So, the discretization in this case, let us take a simpler case where we discretize this whole thing into 2 elements. So, at least this has, say, element number 1, although you can increase the number of elements in each, and then the nodes, let us say this is global node number 1, this is global node number 2, and then this is 3. Spring I am going to account in through the boundary force. So, I am not taking that as a separate element, although one can do that as well. So, these are the 2 elements. So, when we know at element level we have derived the we already know the stiffness matrix, mass matrix, and equations of motion, and let us neglect damping for the time being. So, first step would be the assembly. So, now in the assembly, since this is a dynamic problem, in addition to restoring forces, you will also have inertia forces. So, let me first put the inertia mass matrix into acceleration vector, and then you have restoring forces, which is stiffness matrix into displacement vector, is equal to right hand side. Right hand side now, since we have only the concentrated force P there, so it would be only through the internal forces. And let us say although these points are constrained, this here and this side there. So, let me say that the displacement of this point is u1, global displacement. So, its corresponding acceleration is u1 double dot this is say u2 double dot, and this is u3 double dot. So what we are saying that no, this point is having displacement u1, acceleration u1 double dot, this point is having displacement u2, acceleration u2 double dot, similarly this point is having displacement u3. These are global degrees of freedom, u3 double dot. Those are accelerations. One can also introduce velocities, but we don't need that. So, and here you have no u1, u2 and u3 coming from restoring forces. So first, if you want to assemble if you look at the connectivity, so the first element, its local node 1 is corresponding to global 1 and local 2 is corresponding to global 2. So the mass matrix of the first element will go into first 2 rows and columns of the global matrix. And as you remember, the mass matrix for this element would be, so you can look at your notes. So we had derived it as for a general case rho L by 3, rho L by 6 and like that. So since here A is double, so it will be actually 2 rho A L. L is the element length, capital L, divided by 3, and then you have 2 rho A L by 6. 2 is because no area here is twice, otherwise we had this as rho A L by 3, rho A L by 6. So that's the first row of the mass matrix of the first element, and the second row would be 2 rho A L by 6 and then 2 rho A L by 3. So this is a contribution of mass matrix of the first element to the global matrix. Then if you look at this one, so that is simply diagonals are rho L by 3 and off diagonal elements are rho L by 6. So but its local node 1 is corresponding to global 2 and local 2 is corresponding to 3. So its contributions will go to second and third rows and columns. So you will start here. Let me change the color. So this is plus rho AL by 3, that's the, and then the rho AL by 6, and here of course there is nothing, so it would be 0. Here also it would be 0. Then rho AL by 6 and rho AL by 3. So the blue ones are the contribution of second element, mass matrix. So this is finally assembled mass matrix. This pink color is first element and the blue color is the second element. Similarly, coming to the stiffness matrix, same way you have EA by L minus EA by L, but A is 2, so here you will have 2A by L minus 2EA by L. That's the first row of the contribution of the first element to the stiffness matrix, and minus 2A by L to EA by L. So that's the contribution of first element. We are discretizing both these bars using one-dimensional two-noded truss element, and then taking the contribution of the second one. Here you will have, so now let me change the color. So plus you will have EA by L, then minus EA by L, this separate one. Here it is 0, here it is 0, minus EA by L and EA by L. So this becomes your assembled stiffness matrix. So the mass matrix is stiffness matrix, and then this side. So if you recall, in terms of the internal load, because we don't have any distributed force here. So this is minus Q first node, first element, and then the second node of the first element, and then you have the contribution coming from the second element, so which is minus Q12, that is first local node of the second element, and then here you will have second local node of the second element. So this is the internal load vector, because distributed force is 0, so the contribution due to that here is going to be 0. So this is what you have as your assembled system equations. Now if we look at this is as it is without thinking about any of the boundary condition here, that is this end and the spring this side. One can also do this, take spring also as another element and can solve the problem. I am going to include the effect of spring through this force. So now if you look at the boundary conditions, see the boundary conditions are, one is that if you look at the left end, that is this is fixed. So u1 is 0 at all time instances, so that is u1 is 0 at all time. So u1t equal to 0, since it is 0 at all time instances, So its derivatives will also be 0. So that is u1 double dot, that is d2 u1 by dt square at all time will also be 0. So that is one boundary condition, that is at left end. And then if you look at the equilibrium, just the free body diagram of node 2, so there is a concentrated force P there. So the way we were doing earlier, so the second condition would be that this Q21 minus Q12 would actually be equal to P. That is no, this no, you just draw the free body diagram of this as we have been doing earlier, so you can refer that back. And the third is no, the spring effect. So if you look at no, this particular element, so again I will remind you that no, if you look at no, the second element in terms of internal forces, its free body diagram. So what you have is what we use here, this no, Q12 is actually a force in this direction. So this is my Q12, that is for the second element, and this is Q22. No, that's basically no, this element. So this is the internal force as per our notation. No, this minus this plus this minus this plus. So now if you look at when there is a displacement, and assuming that when the bar is undeformed, the spring is free. So because no, this U3 positive U3 is towards right, so the spring would be under compression. So actually no, this spring would exert a force at node 3 in this direction. So actually no, this Q22 is equal to, so Q22 will be equal to the spring force, which is because for a positive U3, assuming that no, U3 is positive, it can turn out to be no negative, but as a sign convention we are taking U3 as positive, so the spring would be getting compressed, so it would be exerting a force at node 3 in this direction, which is actually negative of this Q22. So you can say Q22 is minus, and then the spring force would be K into U3. So K is the spring constant, which is here expressed in terms of EA and L. So that is minus EA by L into U3. So this is the Q22, that is the spring force which is exerted at node 3 of no, the local node 2 of the second element. So with these boundary conditions, now see what we would like to do is, again as we know here, no, U1 is prescribed, that is U1 is 0 at all time instances. So first again what we can do is take the second and third equation and solve for basically these displacements or whatever we want to do, and then later no, we can solve for the corresponding unknown reaction, this Q11. So now if with this boundary condition, if you take the second and third equations, so take basically you are eliminating U1. What we get is essentially taking the second and third equation. So second and third equation means then you get only the second and third rows and columns. So from the mass matrix, what you will actually get is, as you see here, this is 2 rho AL by 3 plus rho AL by 3, which is actually rho AL. So what you have here is rho AL, and then this is rho AL by 6, rho AL by 6, and then this is rho AL by 3. This is, I am taking the second row and second column, U1 double dot is 0. So when I multiply this with the U1 double dot, I get 0. So there is no contribution from this term, and this is anyway 0. So 0 into 0. So this is what you get here, and then here you will have U2 double dot and U3 double dot. Plus similarly from this stiffness matrix also you are taking the second and third equations. So you get the after elimination of U1, here you get 3EA by L. So 3EA by L, that is the this particular element, this 2 plus 1, 3, and minus EA by L, minus EA by L and EA by L into. So this actually we have been doing earlier, so same thing, only thing is now we have included this mass matrix, that is inertia forces, that's the only thing, and is equal to this side, see this Q21 minus Q12 is equal to P, so this is P, and Q22 is minus EA by L into U3. Since this particular force involves U3, which is an unknown, so we would like it to take to the left hand side, and since this is in terms of u3 not u3 double dot, so this, and it's the second, no, here you see the, now in this equation this is the second row, so it will actually be getting added here with this equation. So what you can do is you can take this term from here to this place. So what you can do is, I will not write the whole thing again, so first thing remains as it is into this u2 double dot and u3 double dot is plus the second one is getting modified. So you have plus this mass matrix, the stiffness matrix 3 EA by L minus CA by L, and here also minus CA by L. And now this is, see, already if you look at the second equation, it's actually rho AL by 6 into u2 double dot plus rho AL by 3 into u3 double dot minus CA by L into u2 minus CA by L into u3 is equal to minus CA by L into u3. So that term you are taking to the left hand side, so it would be getting combined with this. So you will have EA by L plus EA by L, so actually you will get 2 EA by L here, and then this is u2 u3, and then the right side, now since we have taken this to the left hand side already, so what you have is Pn 0. So this will be the final equation. So you see that stiffness contribution due to the spring is getting added into this third row and third column of the original system, second row and second column of this system with u1 eliminated. So this is what finally you get as the equation, and in this equation you will see that it is in terms of two unknowns u2 and u3, which are of course functions of time, both u2 and u3. So this is the final equation. Usually we write this as, after eliminating the specified variables, we can write that this is mass matrix rather than writing every time this. So this is m, and into global acceleration vector now consisting of, in this case only u2 and u3 double dot, and plus this is the, say, global stiffness matrix k into d is equal to, this is, let us say, load vector f. So this is your final system where m is this mass matrix and d is this, k is this, and d is obviously this, as you see, and f is this. So this is the final equation we have, and this you can know in a similar manner for any problem. Let it be the truss, or a 2D truss with a transformation, or beam, Euler-Bernoulli beam, or a frame element, or the frame in general oriented, the different elements along different directions. The procedure of assembly, elimination, and then finally arriving at this equation is going to be same. So you should be able to do this for any given problem because the approach is similar. So I just want to demonstrate for one case. Now if we look at different kinds of analysis, so what you do is typically, although this is going to be brief, so this you should be doing more in maybe a dynamics course, or even some part of it, particularly the algorithm in mathematics and computing course. So here if you look at free vibration, so in case of free vibration, what do? You want to analyze how it is vibrating when there are no external forces continuously acting on the system, although initially there has to be some disturbance or excitation of the system. So you give initial conditions and then leave it. So the way it vibrates, you call it as free vibrations. So in case of free vibration, what you do? Actually this f is taken as null vector. So that means you don't consider any external forces. So f is equal to a null vector, no external forces, and then the resulting governing equation is simply going to be this m into d double dot and plus k into d. This is equal to a null vector. So this you solve. Now again in this there are two things. You might want to do a transient free response, that is given initial condition with time, how the displacements, in this case vector d and d dot d double dot, they are changing. So our other is to find out the natural frequencies and mode safe. So that is known as modal analysis. So now in this, if you want to do modal analysis means just you want to find natural frequencies and mode safes and corresponding mode safes. So in this, what you do, you assume that the motion is harmonic. It's a linear problem. Of course, nonlinear problem, the motion may not be harmonic. So here one assumption we make is that motion is harmonic. harmonic means you can take D as either some amplitude vector into cos of omega t or sine of omega t, where omega is the free vibration frequency. So motion is harmonic. This means that I can take D. So for a general case, I can take this D as amplitude vector. So see, this D is a function of time. Now I am separating out time. So this amplitude into e to the power say I omega n into t. So this includes both essentially cos omega nt as well as sin omega nt. Although final equation what we want is you can also get simply taking D as D into cos omega nt or D into sin omega nt. So I am for a general case where I is square root of -1 and t is time, as you know, and omega n here is actually now the free vibration frequency, which we call as natural frequency. So if you substitute now this solution in this particular equation, so finally what you get is from this equation I can write my d double dot. So you differentiate that twice. Once it would be capital D. Now it's independent of time, capital D, this amplitude. So it would be I into omega n into and then again you differentiate one more I into omega n. So I into I would be -1. So you will get actually this as minus omega n square into D. So this is what you get into e to the power of I omega n into t. Now if you substitute this here in this particular equation, and so again the same logic that when I put it here, so I get minus this m omega n square is a scalar, I can write it anywhere, so I can write at the beginning into d, and e to the power I omega n t of course remains there, and plus k. Of course I cannot write capital D before m, because that matrix vector multiplication has to be valid. So k into capital D into e to the power of I omega n t is equal to, right side is a null vector. Now since if you look at here, this left hand side must be equal to a null vector at all time instances. So the coefficient of e power I omega n t must be actually equal to 0. So this gives you finally the condition that minus omega n square m into d is plus k into d is equal to a null vector, or you can write this as omega n square into m into d is equal to k into d. So now this is what we get. We can, from this equation we can find out omega n as well as d. So omega n natural frequencies, d is the mode shapes. So of course d would, for each frequency this d is also going to be different. We call this as generalized eigenvalue problem. Generalized in the sense you might have done like a into x is equal to lambda into x. So that is a standard eigenvalue problem. So yeah, of course you can do that in this itself. So now if you multiply by m inverse both sides, so then you get omega n square into d is equal to m inverse k into d. That would be a standard eigenvalue problem. In this form we call it as a generalized eigenvalue problem. And there are different algorithms to extract for large size system. There are different algorithms to get omega n and the corresponding d's. And in this case, for a simpler case, what you can do now for the non-trivial solution of this equation, the determinant of so far non-trivial solution of, let me call say this equation A of equation A, we must have determinant coefficient of the determinant of the coefficient matrix must be equal to 0. So I can again take one onto the other side, so get the overall coefficient matrix. So I can as well write k minus omega n square into m. Determinant of this coefficient matrix must be equal to 0. If the determinant is non-zero, then you get d trivial, which is a null vector. And by expanding this determinant, then you can set up basically a polynomial equation in omega n, and then you can solve it for omega n. And once you solve for omega n, then you come back here and get the put the value of omega n here and get the d. Obviously, in D you will have to do some scaling, so in terms of one parameter you can express rest of them, because all the equations here are not going to be independent. So this is how you do your modal analysis. This is same as in the continuum mechanics or solid mechanics. You find out principal stresses and principal stress direction, so there also you solve eigenvalue problem. This is the similar problem here as well, that you are trying to find out the eigenvalues which are omega n values and eigenvectors which are D. So this is known as modal analysis. So you should be, for simpler system, for example for this case you should be able to, so once you have this mass matrix which is 2 by 2 and the stiffness matrix 2 by 2 finally here, so you should be able to write the equation for this determinant. So you will get an equation involving omega n power 4 omega n square, and you should be able to solve that equation first in terms of omega n square and then omega n values. So that is how you get the natural frequencies and mode saves. So maybe if time permits, I don't know whether in the mathematics and computing course did you do some eigenvalue extraction algorithms? Did you study eigenvalue problems in mathematics and computing course? Yeah, but one is that what is eigenvalue problem, so I think that is simpler, but then what are the different algorithms for large size systems for extracting eigenvalues in the corresponding mode safe. So did you do that? MTech students I am asking. Pardon? Okay. So largest and smallest eigenvalue, that kind of okay steps you have done. So maybe depending on, let us see how much time we get. So right now I am going to leave it at this place, that you have to find out the omega and different omega n values, and then back from this equation you find out the corresponding D. So natural frequencies, lowest one usually referred to as fundamental frequency, and corresponding mode is known as fundamental mode. So then next is, so here we were saying that in free vibration you want to do a modal analysis wherein you basically solve the eigenvalue problem, and you may want to do the transient response analysis. So that I am going to do for a general case. So the next is including free or force. So next I am going to discuss, that is transient response analysis. So here what I will do is including the damping, let us rewrite the general equations of motion, m into d double dot. Another of course important point which one can look at it is the original system here. This is actually original system is a continuous system, so it has infinite degrees of freedom, will have infinite number of natural frequencies and the corresponding mode shapes. Now by discretizing this into two elements, finally what we are doing, converting that system with infinite degrees of freedom into a 2 degree of freedom system in this particular case. Of course, if we increase the number of elements, we will get a system with higher number of degrees of freedom. So right now with 2 elements we have converted finally this into a system with 2 degrees of freedom. So in this case we will get out of this 2 natural frequencies and the corresponding mode shapes. Basically 2 omega n squares would be kind of different than finally distinct eigenvalues are going to be only 2. And but if I discretize this into more number of elements, so I will get the dimensions and the sizes of these matrices, then is going to be increased, and then accuracy of these mode shapes and the corresponding frequency will also increase. Of course, sometimes if our interest is only in first few natural frequencies, and that is in general the case. So a lesser number of elements should be good enough. But if you want to look at the highest frequency, then you might need to use a large number of elements. So you should keep in mind that we are converting a continuous system into a system with a discrete system with finite degrees of freedom. So you can expect that when you are talking of static problems, usually you require much lesser number of elements. But in case of dynamic problems, when you want to extract higher frequencies and mode shapes, you require usually large number of elements, depending on if your interest is only to extract maybe say first 5 frequencies, you might require lesser number of elements. But if you have to extract say first 20 frequencies, so then you have to actually use a much larger number of elements to accurately estimate first 20 natural frequencies. So this you should keep in mind, that we are converting a continuous system into a system with finite degrees of freedom. So there is a loss in accuracy, and to achieve desired accuracy, we have to increase the number of elements. So now coming to this transient response analysis, we know how to get mk. So m, finally the equation is going to be of this form. At any time t, the equation of motion would be m into d. We include the damping the way I had discussed in the last class. So this will be plus k into d is equal to f. This is the general equation of motion. Keep in mind, after eliminating the basically primary variables which are specified, and secondary variable in terms of specified external concentrated forces and so on, we get finally this as our equation. This is at any time t, we refer to this as equation of motion of the system. Of course, with the limitation that now the continuous system is represented as a system with finite number of degrees of freedom. Now in this C, usually as I had mentioned in the last class, we take it as Rayleigh proportional, based on the Rayleigh proportional damping model, alpha into m, that is, it's a linear combination of mass matrix and stiffness matrix. So this is a scalar number which needs to be determined based on the experimental data, and beta into k. Maybe sometime I will discuss how to get alpha and beta from the experimental data, but first let me talk about what I want to discuss with this here. So if we want to do a in general, see in the previous case you are only able to get what the if the system is excited and left free to vibrate, so then at what frequency it is going to vibrate and what would be the shape of vibration. That is what you get in the modal analysis, but you don't get exactly what is going to be the amplitude. That comes through the transient analysis. So here we are actually trying to study the transient response with magnitude as well, not just the shape. So this is what we want to do. So we need to do this, and now if you look as it is, in an although in a continuous system, now this d is a function of time, d dot is nothing but essentially the derivative of d, and d double dot is a second derivative of d. So d is a one function of time, but when we are talking of numerical solution of this, so here what we are talking about is numerical solution. Numerical solution means what? Now you are going in the time domain, so this is time, somewhere you start at say t equal to 0 and you choose certain time interval. So you get the solution say at delta t, then at 2 delta t, and so on. No, like that you go, and then somewhere no you have say solution at t minus delta t, then at t, and then at t plus delta t, and so on. No, then you continue like that. So what we want is, now rather than getting a actually exact, now in case of this particular differential equation, obviously now this is a set of simultaneous ordinary differential equation in time domain, because no, it involves only unknown is time. I mean the unknowns are only functions of one independent variable, that is time. So this is an ordinary differential equation, but they are coupled, because they are set of simultaneous ordinary differential equations. So now what we want is, we want the solution starting with t equal to 0, where we will know the initial conditions. The initial conditions are typically at this place what you would know, that d at t equal to 0, know that your d at t equal to 0, say at t equal to 0 will be known, and also velocity d dot at t equal to 0 will be known. So these are your starting condition. Of course, once these are known, and of course you would know this force as a function of time, so you can always work out d double dot at t equal to 0 from this equation back again. And then starting with this, then you want to find out d dot and d double dot at t delta t, then d dot and d double dot at 2 delta t, and so on. That is how you want to proceed. So in general, knowing the solution say up to t minus delta t and t, you want to find out what would be the solution at t plus delta t. So that is a problem. But now this is a numerical problem. So if you numerically look at these values, we are not trying to look for a d which is some close form function of t. So we have three unknowns. Now you see d and d dot and d double dot. So let us say if I have got the solution up to time instant t, and I want to get the solution at t plus delta t. So at t plus delta t, in this equation I will have unknown as d, unknown as d dot, unknown as d double dot, because I am looking at numerical values. So I cannot say that simply my d dot is just derivative of this d, because this is just I am looking at value at this particular place. So now if you look at this equation, this is only one equation, but I have three, d dot, d double dot, as well as d. So I need two more equations. So that is where now the different numerical techniques come into picture for for the numerical integration of these equations. And of course, what we have is the second order differential equation. You have somewhat similar but different algorithms for first order system, where if this is 0, only the first derivative term is present, then you have a slightly different algorithm. So in this category, when we want to do this, we have two set of numerical integration schemes. So one set is known as explicit integration techniques. This is actually numerical integration what we are doing. So explicit integration techniques, and another ones are referred to as implicit. So main difference is, in case of implicit, you consider the equation of motion. Equation of motion is considered at time t to get solution at t plus delta t. So what we do here, that when I want to find out this d at t plus delta t, what I will do is consider the equation of motion, that is this equation of motion at t, not at t plus delta t. So in case of explicit technique, so that is what you do. And one of the very popular in structural dynamics and even large deformation, and most of these packages like Abacus, explicit, and LSDyn and so on, you mostly use what is known as central difference technique. So one of the example under this category is central difference technique. So in central difference, what you do, that first is you are considering the equation of motion, that is basically this equation at time t. So what is the meaning of that? That m into I take d double dot at t, because d is a function of time and we are calculating this, all these variables are discrete time instances, that is 0, then delta t, 2 delta t, 3 delta t, t minus delta t, t plus delta t, what I had shown here in the time scale. So this is now, but this I am talking of explicit integration technique. So in this, the equation of motion is considered at t, so that means all the acceleration, velocity and displacements in this equation of motion are written at t. So into c, into you have d again dot at t, and similarly k into d at t. That discrete time t is equal to F also, the external force at time t. So this is what you are doing. Now what you do in case of central difference scheme, you represent all these variables. So since we are considering this equation of motion at time t, so I will have, say, here t minus delta t, then here I will have t, here I will have t plus delta t. Of course this side you will go, this side will be here. So in central difference, as the name suggests, that the derivatives are replaced in terms of central difference scheme. So now your d dot here, and then what you do, although we have got the solution up to t, but we still express d dot and d double dot in terms of the values of d at this time instant, this time instant and this time instant. So that finally we have equation in which d at t plus delta t is present, so we can solve for it. So now this d dot using the central difference scheme at time t is written as, using central difference means I want to find out d dot at this particular location, so I will take the difference of d at this time instant and divided by the time interval. So this would be d vector at t plus delta t minus d vector at t minus delta t, that is here, and divided by 2 delta t. So I am replacing, see this d dot, I am going to replace this d dot by this, which is nothing but the central difference. So you are approximating this derivative using central difference. I also need to replace this using central difference scheme. So for that I also need to write this d double dot at t. So what we do is, because finally we want to write that also in terms of the vector d, values of vector d at different time instances. So first what I can write is this, so that I am confined only between these three, among these three time steps, t minus delta t, t and t plus delta t. So d double dot at t, first I would write d. So I want to evaluate here d double dot, so I take d dot at this point minus d dot at this point, and then these d dots are written in terms of intern d values here, here and this point. So first I would write this d dot at t plus delta t by 2, that is I am taking this as the center point, and minus d dot here, so which is d dot t minus delta t by 2, because no, this is point t, this point is t plus delta t by 2, this point is t minus delta t by 2, and now the time interval between these two is also delta t. So you divide this whole thing by delta t. Now further what you do, you write this now d dot at t plus delta t by 2 in terms of value of d here and value of d here. So this you can write then subsequently, this 1 upon delta t let me write outside. So then here you can write it as say d at t plus delta t, that is this particular quantity, d at t plus delta t minus d at t divided by, again the interval no between these 2 points is delta t, so divided by delta t, minus no this d dot at t minus delta t by 2, that means I want to write d dot here can be written as d here and d here difference. So then no, you can write that as d at t minus d at t minus delta t, and again divided by delta t. So this whole thing is again the minus sign is common to whole of this. So let me put that minus sign here is equal to this. So now as you see in this equation, you can take this delta t common here, so you can write this as 1 upon delta t square, and then here you will have is d at t plus delta t, and then I have minus d at t, again here also minus d at t, so minus 2 d at t, and then this minus minus you will get plus, so plus you will have d at t minus delta t. So what we have got? We have got this d at d dot at t and d double dot at t, finally all of them expressed in terms of values of d at these 3 locations. So now d here, d here, d here. Since we have already solved this problem up to the time t, so that means we already know actually d at t minus delta t, d at t. What we want is find out this d at t plus delta t. So now these two, let me say that now this is equation b, and this is, I think I have given some name b there, so let me a already. So let me call this as equation b. So let us say this is equation b, this is equation say c, and let us say this is equation d. So if you substitute equations c and d in b, substituting equations c and d in equation b, what do we get? Yes, what do we get? You are going to substitute here, you understand. So this is the equation at time t, actually at that instant we have already got the solution, but in explicit we are considering the equation of motion at that time instant, and then replacing these two derivatives in terms of values of d at different time instances using central difference scheme. And so finally we will see that in this equation we will have unknown d at t plus delta t, which we are looking for. So now as I said initially, in this discrete equation there are 3 unknowns, d dot and d double dot. So this is one equation, we need 2 more, so one equation is here and the third equation is here. So now we have number of equations equal to number of unknowns, so the problem can be solved discretely. So if you substitute that, so first term is m, and into you have d double dot at t, d double dot at t is written in terms of the values of d at different time instances. So again let me write delta t square here. So then here what you have is d at t plus delta t minus 2 d at t, and plus of course d at t minus delta t. So that is the first term. If you look at the second term, then c into d dot, so which is 1 upon 2 delta t into c, and then this is d at t plus delta t minus, I have written, no, that is nothing but your equation c, this equation, and you are putting this in the equation of motion. So this is d at t minus delta t, and 2 delta t I have already written there, the stiffness term, restoring force term is kept as it is, k into dt, and is equal to right hand side you have f at time instant t. So now if you look at in this equation, the unknown vector is d at t plus delta t. So I want to keep this on the left hand side and rest of the known quantities on the right hand side because they are known. So you can, what you can do is one term is coming this one, and from the damping one term is coming from here. So I can write now this whole thing as like 1 upon delta t square into m, and let me also take this term, so plus 1 upon 2 delta t into c, this whole matrix into what I have is d at t plus delta t. So this, because this is an unknown, we don't know d at t plus delta t, we know d up to t. So this is unknown, we are keeping this term on the left hand side is equal to, then right hand side you will have rest of the things. Rest of the things means these two terms multiplied with mass matrix, this term multiplied with the c, and then this term, and of course f. So we will have f at t, and then this term here, so minus 1 upon delta t square into m, and then what you are left with is minus 2 into dt plus d at t minus delta t. You will see that no, all these are known because no, we know the solution at time t, we know the solution at t minus delta t, so this would be known. So these two terms, that is these two terms with the multiplied with the mass matrix are taken to the left right hand side. Similarly here this one, so that you can write say minus minus plus 1 upon 2 delta t into c and into d at t minus delta t. So this is the second term. Minus you have this k into d at t, and f is already written. So this is the final equation. Right hand side you will see that everything is known. Why? Because we know force as a function of time, so we can evaluate that at any time instant. We have already got the solution up to time t, so we know this, we know this, we know mass matrix, so we can multiply this matrix with this vector and get the contribution of this to the right hand side. Similarly this. So finally, to solve for d at t plus delta t, we need to solve now this equation. So we have ultimately this right hand side. Let me simply call this as some r, and this is the right hand side at time t, so I will call this as simply r at t. So you will find finally, and let me see this whole thing as say some matrix, let me call it as m bar. So this is m bar into d at t plus delta t. You can use any notation where m bar is actually this and r is this entire quantity. Now to get d at d at t plus delta t, we need to solve this simultaneous equation. And now the advantage of, we can discuss the advantage of lumped mass matrix. So now let us consider a case. So let us say that the damping is negligible. So now if damping is negligible, or the effect of damping is rather negligible, so that means you are approximately taking C as a null matrix. So if damping is negligible, so what you will have this your m bar, which is now coming here, m bar is 1 by delta t square into m plus 1 upon 2 delta t into C would be simply 1 upon delta t square into m. And of course right side you would evaluate as it is. So once we have this form of m bar simply in terms of mass matrix, and if we diagonalize the mass matrix, now if we use this as a diagonalized mass matrix, which is actually a lumped mass matrix, then when we are solving this equation, let me also name this equation. So this equation is let us say E. Now when we are solving E for this case, if the damping is negligible, that is C equal to 0, then m bar is this. And now if we use diagonal lumped mass matrix, then no solution of set of simultaneous equation required, or rather no, I will say that solution of simultaneous equations is not required. Why? Because then in these equations there is no coupling. Because the first equation you can simply get d1, the first degree of freedom, second equation will get d2, third equation will get d3 and so on. There is no coupling because the mass matrix is simply a diagonal mass matrix. So that is where most of the time you use lumped mass matrix in case of, particularly if you are using explicit dynamics, large deformation, high strain rates and so on. So use actually this central difference scheme, explicit scheme. Wherein because when you are interested in large deformation dynamics, which is more of a transient phenomenon, then the effect of damping would be negligible in that case. So you can just diagonalize the mass matrix. If you diagonalize the mass matrix, so solution of simultaneous equations will not be needed. So the solution scheme overall becomes much faster. That is, you would ultimately see that when you do the finite element solution of any problem, most of the time is actually spent on, major portion of the computational time goes on solving simultaneous equations. And in this scheme, because with the lumped mass matrix, diagonal lumped mass matrix, the solution of simultaneous equation is eliminated, so the solution becomes much faster. So that is why mostly use for many problems this explicit numerical integration scheme because of this advantage. And that is why I was talking about lumped mass matrix, diagonal lumped mass matrix. Its advantage actually comes here. And why it has happened? Because your restoring force because of this k into dt has gone to the right hand side, because we considered the equation of motion at time t. At that time instant we already know this d at t. So that's a known quantity. And when we look at one example I am going to take from implicit integration techniques. So when you would develop the similar kind of final equation of this form based on implicit integration technique, you will find that left hand side, the kind of m bar kind of a matrix would also involve stiffness matrix. And stiffness matrix you cannot diagonalize, otherwise it will not give you the correct restoring force distribution within the system. So then there it becomes mandatory to solve the set of simultaneous equations. So from that point of view, then it becomes computationally more involved. So I will stop here. We will continue in the next class on the implicit integration technique. What we did today is one example of explicit integration technique. If you have any doubts and questions, you can ask outside.